Okay, good morning, afternoon, and good night, everybody. My name is Alex Sanchez, and I'm going to be giving the Advanced Topics Seminar webinar for the coastal modeling system. I just want to check that everybody can hear me okay. How about this? Is this better? I'll try to raise my voice. Okay, good. So I'm going to give a few minutes for anybody else to join. So please bear with me. Okay, so I think I'll get started now. Today is the first day of the webinar, and I'm going to give a brief overview and an introduction to the coastal modeling system, a few slides. It looks like a lot of people on the attendees list also attended the basics webinar last week for the CMS that Mitch Brown presented, but just in case there's anybody new, or maybe I'll add some things that Mitch didn't cover last week. Then I'll give an overview of the documentation, the web documentation, the wiki, the CERT website, and point everybody to the workshop material for this week. And then I know the symmetry and the basic parts of setting up the model and running the model were covered last week, but I would like to review them this week because they're really important, and that's where I see users making a lot of mistakes. And I'll repeat some of what Mitch said, but I'm also going to add some new things today. And after that, I'll start getting into the hydrodynamics. I'll cover really in detail the theory, numerical methods, and how to, like parameterizations, and how to change them in the input files. Lots of the default settings in CMS are designed for the model to be robust and fast, or to be backward compatible with previous versions of the CMS. So the default settings are not necessarily the best ones all the time for your project. And so understanding the theory and numerical methods and all the options allows you to customize the CMS for your project a lot better. And so Tuesday, I'll probably have to cover a little bit about the hydrodynamics, and then go into the initial and boundary conditions for hydrodynamics, salinity transport, the surface roller. Wednesday will be also going to transport. Thursday will be numerical methods, advanced output, and scripting. And Friday, I'll cover how to debug the problem, debug the model, how to find problems, find what is the problem in your case, if it's a stability problem, or if it's an input problem, if it's a model problem, and talk about model calibration and post-processing. So the focus of this webinar is not going to be a hands-on tutorial as much like the basics webinar was last week. Here we're going to assume that you have SMS experience, and you've used either the CMS or similar models, morphodynamic models in the past, and so you understand the terminology and the basic procedure in setting up a model, what kind of input data you need, and how to analyze it. What I really want to focus on this week is for everybody to understand where and how to find documentation, the tutorials, because you can, once you know that, you can learn by yourself. Because really, learning a model, it just takes a lot more time than it's possible to do in a webinar. I want to focus on the theory and numerical methods because you need these in order to understand the model applicability, so knowing when and when not to use CMS. Before you even start with the project, I get a lot of calls from users and they'll ask me, hey, do you think I can use this model for the CMS? And if I don't think so, I'll tell them not to use it, to maybe try a different one, or point them in the right direction, maybe ask them to talk to somebody else that I think is knowledgeable in that area. And also, to interpret the results, you need to understand the theory and numerical methods. So once you get all these results, you get a lot of information from these types of models. What do you do with it? How do you analyze it? How do you summarize it and reduce it into something that's meaningful? And to do that, you need to understand the model. Calibration, the same thing. I see a lot of people trying to calibrate parameters that maybe are not even related to what they're looking at, or parameters that are insignificant, and wasting their time, basically. So understanding what processes or parameters are more important than others is really important. And if you want to use it for engineering purposes and design alternative cases, then you need to be realistic about the limitations of the model, what you can and cannot do. You can't predict morphology change for 15, 20 years with CMS, for example. Okay, and I want to give, as I go through all of this, tips on how to set up and run the model and analyze the results effectively so that the end result is adequate for the purposes of your project or your application. And also efficiently, that you don't waste time, that you, for effort, that you're organized, and I'll do this from my experience. I'll show how I do it, and you can take it or leave it or modify it for your, as you like. And I have problems with being efficient. I'm really a perfectionist, and sometimes I spend a lot of time on things that aren't that important, like symmetry in areas that are not the project side and things like that. So doing these, even though are the ultimate goal, but it's really hard to do. Okay, so I'm going to look at some of the questions here before I go on. Okay. Okay, so the coastal modeling system, like Mitch covered last week, is an integrated wave current and sediment transport model that is interfaced through the surface water modeling system developed by Aquaville, formerly Brigham Young University, BYU. It is operational at 10 U.S. Army Corps of Engineers districts. It's been verified and validated. It is designed to be robust and user-friendly and practice-oriented so that you can get medium-term simulations done in a few days. And the types of applications it's designed for are deepening, widening, and lengthening of navigation channels, designing or realigning jetties and coastal structures, operation and maintenance studies, and also looking at processes, wave current interactions and things like that. Okay, the CMS is freely available. It's downloadable from the SERP website. It also comes with the SMS installation, and the interface isn't free, but it's relatively cheap. You can get academic discounts. I think the coastal modeling suite is about $5,000, so it's relatively cheap. Um, Documentation, we have several forms of this. We have technical reports, technical notes, journal papers, the wiki, and there's going to be 2 new technical reports published later this summer. One on theory, numerical methods, and a little bit about the input and output type stuff, and the other one solely based on the interface part. So the draft CMS manual that I'm going to talk a little bit about later is going to be converted into those technical reports. We offer training. We've done 32 tech transfer workshops since 1997, about 1 or 2 a year. We do additional workshops by request, on-site training, seminars, step-by-step instructional materials like videos and hands-on material. And now webinars. This is the first webinar that we've done, and so I'm trying my best. Okay, so as far as what CMS is appropriate or applicable for, this is a really interesting plot of time and temporal scales, and the point is to show you what temporal and spatial scales CMS is designed to work with, and it goes from about millimeter scale to 10-kilometer scale, spatial scale, and temporal scale from minutes to a couple of years. And that's CMS here, and then the blue color. And there's also the Goose Nest modeling technology, the particle tracking model, and other Army Corps of Engineers models, or CERT models, I should say. Okay, some of the key features of CMS flow are that it's finite volumes, conserves mass, it's relatively stable, it's accessible to scientists like oceanographers like me. I'm not a mathematician or anything. It's coupled with the spectral wave model CMS wave inline, so it's within the same code. It's tightly coupled. It also has inline sediment transport morphology change. By inline, I also mean it's on the same code. And sediment transport is also on the same grid as the flow. We have the capability to do nesting and the typical boundary conditions and forcings that you would expect for a coastal morphodynamic model like tide, river, flux boundary conditions, wind, atmospheric pressure forcing, and things like that. It's also integrated with the particle tracking model in SMS 11 and 11.1. It has 2 types of grids available, well, basically 2. Actually, these can be subdivided, but you have the option to do a non-uniform Cartesian grid or a telescoping grid. And whether you choose one or the other depends on basically time, and because the telescoping grid is more involved to generate. The non-uniform Cartesian grid is simpler. And we also have 2 solver options. You can use an implicit scheme, which is designed for tidal flow, long-term morphology change, takes big time steps on the order of 10 minutes, or you can use the explicit solution scheme, which is designed for flooding, breaching, supercritical flow, problems where you have a lot of wetting and drying, and its time steps are on the order of about 1 second. And both codes are parallelized with OpenMP for PCs. Sediment transport, we have 3 models available. The classic external equation, which is the equilibrium total load model, an equilibrium bed load plus non-equilibrium suspended load, and a total load non-equilibrium transport model, which is the new one. And we've had really good success with that one. We support several equilibrium sediment transport formulas, which are listed there. We have the ability to simulate sediment transport over non-erodible beds or surfaces, or hard bottoms. We have avalanching, the bed slope influence on the bed load, and the suspended load surfaction. And in the last 4 years, we've added multiple size sediment transport. CMS wave includes shoreline refraction, diffraction, reflection, bottom friction, lots of features. I think Mitch covered this last week. I won't go into details of that. Recent accomplishments, telescoping grid has been around since SMS 11, so about a year or 2 years. We've also added multiple size sediment transport in the last couple of years, the surface roller, the wave average formulation, offshore sediment transport. And we've done a lot of publications recently, journal articles, the V&D reports with a significant effort. There's lots and lots of test cases on there. The wiki has also been a big effort, and now the new reports that are coming up, the CMS manual and the technical report. Okay, so these are some examples from the verification and validations from the reports I mentioned earlier. They provide benchmark data sets. We're testing the model as we change them or improve them. We can go back to these. We have also applied unambiguous criteria, goodness of fit statistics, analyze how good they are. So we didn't just say, oh, the model looks like it compares well with data. We use goodness of fit statistics to say how good they were, and those are actually in the CMS manual and on the wiki website. The test cases also provide a go-by for applications, especially the field cases. We describe what settings we use, how we set up the model, so if you have a similar application, you can follow those examples. And we identified areas that the model didn't do so well, so areas for future development and research. And a lot of the test cases are on the CERT website that you can download. Great. So these are some examples. These are both verification tests, idealized cases of a circular ocean or basin with spatially varying winds, and this one is a bump with transcritical flow over it, and you get this hydraulic jump on the downstream side. And this case is an idealized inlet, a physical model study that was done here at Waterways several years back, and the one up here, I'm sorry. And we compared with wave heights and the current velocities. And down here, this is a famous laboratory experiment by Visser. We looked at wave heights, longshore currents, and mean water levels. And also field cases. This is an example for Shark River Inlet, which is the site that I'm going to use during this week for the hands-on, not the hands-on, but the webinar. This other case is a laboratory experiment of multiple side sediment transport, where they fed, I should say, sediment from the upstream end. It was a bimodal distribution, and then let the sediment go downstream and sort out and find downstream. So I'll show this animation because I really like it. It's the only animation I'm going to show today. You'll see how the sediment starts going in and how the little rectangles are bed layers, and the colors indicate the median grain size, the G50. So you can see how downstream it starts finding out, and these lines and dots are the bed elevations at different time steps. The blue one, the blue dots, is our water surface elevation. So I'll just let it run. The current velocities are indicated by the green arrows. So as the animation progresses, when it gets to a certain time, it'll overlay the measured data of the bathymetry and water levels. So over here you see a hydraulic jump forms at the end of this. Okay. So as far as the workshop material, if you go to the cert.usace.army.mil under tech transfer and webinars, there's a tab for the advanced topics webinar for CMS. And you can click on that. You see that there's a Oh, I see you have problems hearing. Try to move my microphone up a little bit. Is that better, Mitch? All right. I'll try to put this on my jacket instead of my shirt. Maybe it'll be closer to my mouth that way. Okay. So as I was saying, you can download the workshop material from the CERT website under the Tech Transfer tab and webinars, and then advanced topics for CMS. The workshop material is basically the same as that was presented for the last workshop. And we have a draft CMS users manual. You can download that from the same page as I mentioned previously, this one here, or from the wiki. You can go to cert.usace.army.mil wiki CMS, and then inside the documentation portal, this will be on the right-hand side, lower right-hand side. Let's take this. Okay, so I'm going to go ahead and skip this. On the wiki, I want to point this out. So as I mentioned, the draft CMS users manual is here, but also here there's links to other utilities or downloads, MATLAB scripts, links to other software that we frequently use, and Fortran executables for doing wave transformations from offshore to nearshore and things like that. So I really recommend that you go to this site and look at all these items. Some of them might be useful to you. There's tools for title analysis and prediction, filtering time series, and I'd like to cover this tomorrow if there's time for pre-processing time series. I think that's important. There's utilities for pre and post processing, like I mentioned. Okay. And if you want to learn more about CMS or look at applications with the CMS, you can go to either the CERT website or this wiki website, and there's a list of reports, conference papers, journal papers, technical notes, even theses and dissertations related to the CMS. And here's a list of some examples, not all of them. I'll post this this presentation on the CERT website after the webinar today, so everybody can have it. Before I go on, I'd like to recommend some software and hardware for everybody. First of all, you need to have, if you want to do serious modeling, you need to have a good text editor like TextPad or Ultra Edit, Notepad++, for viewing and editing large ASCII files. Also, if you want to edit or view the XMDF files, which are the binary solution files, and even the grid and the model parameters file, you need to have HDF view. And I also recommend having MATLAB or Octave. Octave is kind of it's very similar to MATLAB, but it's free. So if you can't afford MATLAB, you don't have it, you can also use Octave. I would really recommend that for pre-processing, post-processing, data analysis, and visualization. Lots of the utilities that we make are for MATLAB. Excel is okay, but it's not good for everything. And also, you need a good computing machine. The model is pretty fast, but you still need a good computing machine. Right now, I'm running on my laptop for this audio because my computing machines don't have graphical sound cards, but you need a fast machine. Okay, so now I'm going to go into the documentation. Okay, so Anya wants to explain the wiki. Okay, so some of the organizers here. The wiki has the main page for the CMS wiki is this. Okay, and it just gives a quick introduction. And down at the bottom is the documentation portal, and this is a really nice site, the way it's organized, because it's all there. It has the technical documentation, so the theory and the numerical methods on the left-hand side, and in the middle is all the interface stuff. So how do you do it? Where do you go in the interface to set this parameter? And then on the right-hand side, we have test cases, a glossary, references, the goodness statistics that I mentioned earlier, and workshop material, and different downloads, like the user's manual, the utilities, title constituent databases. There's a lot of information here. We try to keep it up to date, but recently we've been focusing on the user's manual. We want to get that out as soon as possible. Okay. So, if you download the user's manual, this is what it looks like. It's pretty lengthy. It's like 300 pages, and it has the mathematical formulations, the theory on everything, all the numerical methods, and a user's guide, which covers the interface, but focused on the input of the CMS, what the cards are, how do you set the parameters. And we also have in this document a description on how to run the CMS and how to view and post-process the results. At the end, there's lots of appendices describing input and output files. There's examples for multiple test-driven transport, MATLAB scripts, benefit statistics, and even the glossary in here. It's really comprehensive. And this is what I'll be using for the webinar to talk most of the time. I'll be showing you this. I'm not going to do a death by PowerPoint. We're used to doing that. We were used to doing that until last year, and we really decided that it was better to focus on giving people a really detailed document describing all the steps necessary to do certain things, hands-on material, basically, instead of PowerPoint slides. And that's why we focused on developing this document, and it's what I'll be using for the webinar. Okay, so I think before I get into the theory, I'd like to cover, Mitch covered last week how to run the CMS from the interface, and a little bit about how to run it from the command prompt, but I want to revisit that. Because I see a lot of users running it from SMS, and it's okay, but I really recommend against it. It's unnecessary, and running from a command prompt is just so much better. Okay. And that's described in the user guide here, running CMS chapter 4, running CMS Flow. And it starts by describing the recommended folder structure. So how we, or I should say really how I organize project folders to keep everything neat and organized. So in this project file, you see that there is a folder for aerial photographs, which you need, obviously. CMS folder for all the simulation cases. You have case 1, case 2, and then alternatives within those. There's a folder for data, and within that folder you divide into bathymetry, sediments, tides, currents, waves, and wind. So data is measured data. Okay? And then there's folders for figures, like MATLAB figures, references, reports. Sorry, I'm having trouble with the voice here. This is how we do it, and it's what I recommend, but you can modify this to whatever suits your needs. What I don't want people to do is to have one folder with all the files dumped in there. That's really not the way to go, and we even see that. And I'll talk a little bit later about how to save the CMS and the way that we find easier. Okay. So Mitch talked last week about running the CMS from the interface, the SMS, and I'm not going to cover that. What I do want to cover is how to run it as a standalone program. Okay, and that's described in detail in this section. But what I'll do is the hands-on here. So in this document, wherever you see this lady sitting in front of a computer, it means it's the section that has a hands-on section where it tells you, if you want to do this, if you want to open a command prompt in this case, how do you do it? You click here, and then you go there, or you can do this and that. Okay, so I'm going to follow this. I'm going to go to the Start menu, go to All Programs, and then Command Prompt, and that's how you open the command prompt. You can also do it this way. You can go to Run and say Command CMD, and that'll open the command prompt for you. Now, this takes you to a place where you don't necessarily have your project files, right? So you need to go to where you have your files. And the workshop material that I pointed you to that's on the website has a folder that has all of these subfolders, okay? Bathymetry, bottom friction, and so forth. And each folder is designed for you to have an example of how to change the cards or input parameters for that specific topic. For example, if you're interested in modifying bottom friction, you can go to the bottom friction folder and see how it's set up in there and modify that one. Okay. So let's say right now this was my project file. If I wanted to go there, I could copy that and then type that path here. Simple way is by double-clicking on this, you select it, you copy it, and then go to the command prompt and type cd, which is change directory, and then paste that path, and now you're there. Now you can run the CMS inside that folder. Another thing I recommend for everybody to do is to save your executable in the folder where you're running the CMS. And don't keep other stuff in there. Don't keep aerial photographs that you don't need. Don't keep it very concise. Okay. Having the executable within the same folder is good because even though the executable has the version and revision number in its name, if you give that project call to somebody else and it's maybe an old project, they may not be able to find that executable if they want to rerun the model. Okay? So it's always good to save the executable in the same folder where you're running your files. Another thing that I like to do is I like to group the files in Explorer into flow files, CMS flow files, and wave files. And an easy way of doing that is by naming them with something that starts with flow and something that starts with wave. It's very clear to me to do that. If you use SMS and save it as a project, the whole thing, it'll save, for example, Mitch last week was saving webinar something something a dash and then the names. And if it creates a really long name, it saves everything every time you save a project. And I don't like to do that. When I work with CMS, I like just loading what I need to look at and saving what I need to save. Okay, I find that much better. So if I wanted to just work with CMS Flow, let me look at these questions first. I'll just load that, and when I want to save that, I'll say save only CMS Flow. I won't save the project. Okay, that's the way I do it. For running the code, I recommend that you do it this way with the command prompt. There's other ways of doing it. You can drag and drop the same cards file on top of the executable to run it. You can double click on the executable and type the name of the same cards file. Same cards. And run it that way. Okay. There's lots of ways of doing it. And this is really what I recommend that you do. Okay, so now I'd like to talk a little bit. Is there any questions on this before I move on? Okay. Looks like some of the questions are related to what I'm talking about. So I'll let the organizers answer those. I was going to go into bathymetry. Okay. So now that you know how to organize your project and your files, you want to start working with the data. One of the most important ones is bathymetry. So I'll talk a little bit about that. Even though Mitch did, I want to reiterate on that. Okay. So I'm going to bring this one in. Okay, so this scatter set is for Grace Harbor, Washington, and it's the one I used for a recent project that we did there. And you can see that it's a conglomeration of lots of different data sources, multi-beam, single-beam surveys, LiDAR, things like that. What I want to focus on is really using break lines and talk a little bit about resolution. Okay. First, I want to change my display settings so that I can see the contours of the bed of the bathymetry. So I'll turn the scatter markers into black, keep them the same size, turn on the contours, and then the range is important because I want to focus on the near shore, so maybe -1 to 10. Oh, I forgot to turn on the contours. Everybody's advanced here. Everybody knows how to do the display options, so I won't spend too much time on that. But what I really want to show is this. If I triangulate, you can see that there's lots of problems with the triangulation because of the resolution of the data or the way that the surveys were oriented. Like here, the channel has this meandering pattern, which is totally artificial on the data. So if you insert break lines in there, you can fix them. Okay. The way you insert break lines, and you covered that last week, is you have this tool here, which is create scattered break line. And you click on points, create lines. And the break lines will force the triangulations to not cross those lines. And this is really useful for controlling the interpolations and the orientations of those surfaces between the triangles. It makes a really, really big difference. For example, let me show you this area over here. If I retriangulate, this part of the channel was closed, for example. Another issue I commonly see with bathymetry is that people, just because you have bathymetry with high resolution doesn't mean you should use it. The reason for that is high resolution bathymetry, like the divider, has a lot of detailed information that you don't necessarily want the model to have. For example, bed forms. The model does not calculate bed forms unless you have maybe 20 cells per bed form length. And if it doesn't have that, then it's just noise to the model, and they're going to smooth it out. And when you calculate bed change, that high resolution noise is going to turn up as noise. It's going to look like you're going to have a lot of reds and blues. So it's a good idea to precondition and smooth your bathymetry and remove the features that you're not going to resolve with the model. Okay. One way of doing that, looks like there's a question. The screen is flickering a lot. Having trouble looking up. Okay. One way to smooth the bathymetry is to bin the data. For example, multi-beam data, you can bin it, of course, in the resolution, and that will help remove the high frequency features, the bed forms. And when you calculate bed change, your results will look a lot better. Okay? So that's what I did here, for example. This survey here was very high resolution and only along the transects, right? But the transects were spaced 300 meters apart. If you do triangulation with that, you end up with long, very thin triangles, and it looks noisy. Even here, you can imagine if these points were spaced closer together, these effects would be even worse. Okay. And to do binning, we have a utility on the wiki that is called XYBin. It's a MATLAB utility, and that's this here. This is an example of multi-beam data that was binned, and so it looks for points that are within the same bin, and it averages them together. So it's a way of smoothing data, but also not resampling, but thinning the data, reducing the amount of points. If you have a lot of LiDAR data, it can be too large to work with. So you can run it through this and reduce the ambush points significantly. If your cells are 10 meters wide, it doesn't make sense to have sub-meter resolution in your bathymetry. You want to use something like 5-meter bins. Okay? I know Mitch covered bathymetry and scatter sets last week, but I really wanted to cover this again this week because I think it's really important. And once you have your bathymetry, it's really important to zoom in and change the contour so you can see that it looks good, that it looks realistic and reasonable. Okay. All right. And I spent maybe 3 weeks on this particular bathymetry scatter set, and this place still doesn't look as good as I'd like it to. Okay? So it takes a lot of time. I always tell people that when you're going to estimate how much time it's going to take you to do a project, you should estimate about 50% grid generation and preparing the symmetry and such, and another 50% everything else, running the model, documentation, things like that. It's really time consuming to prepare for symmetry. Okay, so I'm going to go back to the user's manual and go to, okay, it's 145, that's good. Hydrodynamics. Before I move on, is there any questions related to this? To accept the lowest real data, there's a question by Chris Weber, and he's asking me if it's possible to set the bin to accept the lowest real data or highest real data. It's not possible, but you can download the scripts, and it's really easy to modify them. Right now, it has a mean function in there. You can easily modify that, change that to a min and max function. That's a really good recommendation, and then I'll look into changing that. Maybe post a new version up there where it gives you the option to select either the min or max. I still see that people are having problems with the audio today. I really don't know what to do. I'm trying to put it up against my nose as best as I can. Sorry about that. I'm going to blame it on Mitch Brown because it's his microphone. Okay. So, actually, before I go into the theory, I want to review a little bit about Chapter 4. Talk a little bit about the modeling process, just to put everything into context. Well, do I want to do this? No, I'm sorry about that. I'm going to go back to the theory because I'm running out of time today. We're not going to go 2 hours every day. I'm going to do 1 hour every day because I think 2 hours is too long for people. Okay, so hydrodynamics. CMS solves the depth averaged hydrodynamic equations, depth integrated and wave averaged equations. In the report we have, we don't give the whole derivation of the equations, but we do give the definitions for the variables and then give you references for the derivation. And then the final equations that the CMS solves are these. So it's a continuity equation and a momentum equation. Includes Coriolis, atmospheric pressure, wave radiation stresses, surface roller, surface stresses, and bed stresses. Equations are very similar to those of Svensson's book, if you're familiar with that. The only difference is the inclusion of the atmospheric pressure and the form of the mixing term. Here we use what we call the total flux velocity, V, which is defined as the sum of the wave depth average current velocity and mean wave mass flux velocity, or simply wave flux velocity. I'll give some definitions of those later. Some questions. Okay. Yeah, so in Svensson's book, he formulates the mixing term slightly different. We chose to do it this way because it, for one, it simplifies the discretization and also is more consistent with the generalized Lagrangian mean formulation. So these are the equations that we solve. And we give some definitions for the variables. H is the total water depth, eta is the water surface elevation, and eta bar is the mean water surface elevation. the wave flux velocity is a water flux it's a fictitious velocity. Basically, it's the wave volume flux divided by the water depth. The wave volume flux is reduced due to two things: Stokes strip, and in the surf zone, the surface roll. So the part from Stokes strip is this part, E sub W, and the part due to the surface roll is this term here. And the mean, okay, well, before I move on, I want to mention that you don't have to run the CMS as, you can turn off the wave, if you turn off the wave flux velocity, then what happens is the total flux velocity becomes the current velocity, and then the governing equations become the typical ones that other shallow water equation models solve, like maybe like ADH or what's another, like RNA, like regular type models, okay? Or even older versions of CMS. Is there a problem with the volume still? Are people having trouble hearing me? I'm talking right into the microphone now. Can people hear me better now? I'm really sorry about this audio. We tested it twice this morning and it sounded fine, and now we're having problems. Is it better now? Talking directly into the microphone. Alright, well, I'm really sorry about the audio. I'll keep going. Okay, the mean wave current bottom friction. When you have a current superimposed with waves, the waves enhance the bottom friction in a nonlinear way. And the way we parameterize that is through this nonlinear bottom friction enhancement factor that goes in front of your typical quadratic bed shear stress formula. And then there's another factor here, which is M sub B. That's the friction coefficient. And I'll show how those are calculated in a second. C sub B is the bed friction coefficient. And in CMS, there's three ways you can input the bottom friction, as Mitch described last week. You can input a Manning's N, the bed friction coefficient, or a roughness height. Roughness height. And the parameter that you input is kept constant, and then the other two are calculated internally at every time step based on the local water depth. And then there's different formulations for calculating sub WC, the nonlinear bottom friction enhancement factor. There's 7 parameterizations for that. There's a simple quadratic formula, 2 empirical curve fits by Solvay, and then parameterizations of other analytical and numerical models from the authors listed here. Pluto, and maybe some Grant and Madsen. Default formula is the quadratic formula because it's the simplest one, and also it gives pretty good results, at least consistent with the other wave current boundary layer model. Yeah. But you can change that in the advanced cards. Okay. Is there a question? Okay, it seems like it's sounding a lot better, so I'm glad. Am I going there too fast? Or is this pace okay as far as talking about the theory? Okay, good. So I'll continue with the bottom friction. Um, okay, the rest of this section describes how we calculate and define the root mean squared error. And this is something a little bit confusing in literature. If you look at RURMS, people define it different ways. The definition that we follow is that of Solti, which is stated here. So it basically is the root mean squared error of the near bottom orbital wave orbital velocity. Some people, however, include a factor of 2 in here because they want to do it analogously to the wave heights. And we don't do that, okay? So it's just something to keep in mind if you're comparing, for example, this equation to others. This square root of 2 does belong there. This is one way of calculating U sub RMS. With HRMS and the peak period, some people use T sub 0, where 0 is a zero crossing peak, wave period. But it's been found that using the peak period is a better approach. It gives you better estimates of URMS. What we've included recently in CMS is this parameterization, which is obtained by a curve fit to integrating the wave spectra, a John-Swap spectrum. So doing this here. Okay, you take a John-Swap spectra and then you integrate it to get URMS. And then you parameterize that based on, so the input parameters are the significant wave height and the period only, which are the variables that you typically have. Okay, and this is much more accurate. That's what we're using now in CMS. Now, going back to that dead slope friction factor that we call, basically accounts for the fact that the bed slope is not flat. The bed is not flat. It's at an angle. And so the bed friction acts on a larger surface area than if it were flat. And this number is always equal or greater to 1. And typically, it's pretty small. It increases with the bed roughness, the bed shear stress by 2 to 5%. But for completeness, for correctness, I like having it there. By default, it's not turned on. So something you can add. Going back to the bottom friction, with current bottom friction model, the default one is a quadratic one. I think I mentioned that. I wasn't sure. Okay, so before I move on, I'm going to go to the user guide part for bottom friction. Okay. So everyone's familiar with how the interface looked at. Mitch covered that last week. Everybody in advanced users. Everybody knows how to create a data set. But what if you want to use one of the advanced options, like another wave current bundler model, or the wave, the dead slope friction factor? How do you change that? Well, there's a description in here of all the cards that are available in CMS, what their names are, the arguments.
If you look at the questions, they want to stop here.
Okay.
See some questions.
Okay, I'm sorry. I was asked to answer some questions before I move on. So that's a good question, Matt. The question is, is the bottom roughness kept constant during the simulation? And the answer is the input roughness parameter that you give CMS is held constant. For example, if you give it a Manning's N, then that Manning's N is constant for the whole simulation. It doesn't add later um, uh, bed form roughness, or if the bed composition changes, it doesn't change that Manning's N. Same thing for the roughness height. The roughness height that you give the CMS as an input is held constant for the whole simulation. Now internally, it needs to calculate the other parameters. Like if you give Manning's N, internally it needs to calculate the roughness limit. And it does those every time step, because if you look at the equations in here, the Manning's N and the roughness length and the bed friction coefficient are all related and are a function of the local water depth. That's what I mean. But the value that you give it, for example, if you gave it a bed friction coefficient, it would keep this value constant, but update Z sub 0 and Manning's N every time step. Does that make sense? Does that answer your question? Okay, good. So going back to the user's guide, if you wanted to change bottom friction, how would you do that? So I don't memorize the cards. There's too many of them. What I do is I look at the manual, I go to the section that talks about whatever topic I'm looking into, and then look at the cards in there. And I can just copy paste them into the same cards file. For example, I could copy paste this into the same cards file. Or for this one, the tables give you all the options available. And in some cases, there's hyperlinks to chapter 2 with all the theory. In the workshop material, there's a folder called bottom friction. If you open that, it already has the cards in there for modifying bottom friction setup. For example, the wave current mean stress, how to calculate that. The default is quad, but you can change that. And then this bottom friction coefficient is, the default is 6, but you can change that too here, and that is this number over here. C sub W. Okay. That's that number. Like I mentioned, I recommend using a good text editor like TextPad or Ultra Edit. I like TextPad, and you can highlight. You can load a syntax file into TextPad, and it's available. The syntax file is available on the wiki of the utilities. Let me go back up here. If you download this file, it has some instructions on how to set it up. And once you do that, and you load the same cards file into TextPad, it'll highlight the cards and maybe keywords and comments inside the file. It makes it a lot easier to look at. I like doing it this way. So if you want to change something simple like a bottom friction parameter, it's a lot easier to edit the same cards file than to load it in an SMS, change it, and save the whole thing again. SMS will save everything, the grid. It's a big grid that you're looking at, over 100,000 cells, and it's going to take a lot of time to load it and save it. A lot faster just to edit the same cards file. Okay. Now moving on to eddy viscosity. After eddy viscosity, I think we'll break for today, and then tomorrow we'll go over everything else, hydrodynamics. In CMS, we assume, well, eddy viscosity comes from the fact that small-scale eddies or vortices are not represented in the model. And so the eddy viscosity concept is intended to simulate that energy dissipation at the smaller scales than your numerical grid. Okay? In CMS, we assume that the total turbulent eddy viscosity is the sum of three parts. A base value, which is close to the kinematic eddy viscosity, a current component, and a wave component. Before I move on, is there any questions on the bottom friction? Oh, okay, I have two questions, sorry. I need to go back a little bit. Allison is asking for recommending a free, powerful text editor. Notepad++ is a very good text editor, and it's also free. If you're Army Corps of Engineers employee, TextPad is also free. Ultra Edit, I don't think it's free for us. And there's another question. Is there a recommended default for bottom friction? So the default method, if that's what you're talking about, bottom friction, is the quadratic formula. Okay, that's this one here. If you're asking if there's a default value for the bottom friction, in previous versions of SMS, the default value for Manning's N was 0.025, but honestly, we didn't like that very much. It's a little high for most coastal applications. A value closer to 0.02 is a better starting point, I think, as a default value. And it does make a difference to use a spatially constant and spatially variable bottom friction. If you know the bed type, whether you have mud or sand or vegetation there, it makes a difference if you use a different Manning's N, and that's relatively easy to do in the interface. In the manual, I give a table of typical roughness heights for different bottom types. But I'd like to augment this table with values for Manning's N and bed friction coefficient. Does that answer your question, Mark? Okay, good. Okay, moving on to eddy viscosity. Like I said, the turbulent eddy viscosity is the sum of three parts: the base value, current part component, and a wave component. The current-related eddy viscosity, there's four options to calculate it. There's the Faulkner equation, which was the formula that was used in the previous versions of CMS, so we kept it there. There's a depth average parabolic model, which is typical of like vertical-type models. There's a subgrid model, which has two parts: the part due to the bottom shear and the part due to gradients in the current velocity field, which is this part. So it's Mogrinsky type model. And this is the default model in CMS. It's pretty accurate and it's efficient to calculate. The mixing link model is pretty good. We've seen that it works better than the subgrid model for some cases, but I don't know what happened here to the equation. But it's more computationally intensive. I think for rivers it's a really good model, but for coastal problems, subgrid is better. That's why it's the default. The wave-related eddy viscosity also consists of two parts. One is due, well, it represents the turbulence due to bottom friction, and the other component represents the turbulence produced by wave breaking. So D sub BR is the wave breaking dissipation directly from the wave model from CMS wave. Okay. Is there any questions on eddy viscosity? Nope. Okay, so I'll go to the user's manual and explain how you change the options for the eddy viscosity. Right now, the only option in the interface in SMS 11 for eddy viscosity is to basically turn mixing on or off. And these options are options that were inherited from when the SERP was using AdSERP, and AdSERP was having trouble running with these terms. People wanted to turn them off to see if they could get it running. So really, for practical applications, it doesn't really make sense to turn off advection and mixing. One way you can turn off mixing is by modifying the coefficients to the model. Like you can set all the coefficients to 0, the base value to 0, and then you have 0 mixing. But we don't recommend that. These are going to be removed in SMS 11.1. Right now, if you want to change the eddy viscosity calculation, you have to do it through the advanced cards. And these are the cards that are available right now. If you go to the workshop material, there's a folder for eddy viscosity, and there's an example there of how to use them. So pretty straightforward. I think by now you're getting the idea of how I'm going about this webinar. Let's see. As far as the manual also has notes and tips. For example, what happens if you change the eddy viscosity? It talks a little bit here about how it affects your results. Increasing eddy viscosity is going to widen the Longshore current distribution. It's going to widen the ebb and flow jets at inlets. And it smooth out small gyres and recirculation zones. It's important to note that eddy viscosity also affects sediment mixing, because the mixing coefficient for sediment is a function of the turbulent eddy viscosity of flow, and includes the Schmidt number, which I'll talk about these things on Wednesday, more about those things. One last thing for hydrodynamics, and I think we're going to call it a day, is the wave mass flux, which I talked a little bit about, how you can activate that. So the wave mass flux has two parts, like I mentioned, the part due to Stokes drift, which is always on, and the part due to the surface roller. The part due to the surface roller is only activated if the surface roller is on, the surface roller model is on, and you turn on that card. By default, as this table mentions, both are off. So the governing equations that you saw were the same ones as previous versions of CMS. Because this wave average formulation is new, relatively new. Okay. If you turn on the wave average formulation by setting the wave mass flux to on, then when you look at your, let's say you have an open coast with an equilibrium beach, you look at your current velocities, the current velocities are going to have a component offshore, and that's due to the undertow. So if you go to the field and you put an instrument in the surf zone, that's what you would see. You would see a component going offshore due to the undertow. And if you run others, if you don't use the wave average formulation, then the currents will just be parallel to shore. I see some questions. Is there any major differences between SWAN and CMS wave? There's very similar models in that they solve the same equation, the wave action balance equation, but the way they go about solving them is very different. The numerical methods and the parameterizations for lots of the processes, like wave generation and bottom friction, setup, lots of things are very different. But for details on that, I would recommend that you talk to Li Hua Lin, which is the wave modeler here with our group, or executive market rate. I also recommend that you read the verification and validation reports, because we talk about all of these things, the wave average formulation, the bottom friction, and we say which ones we used for each application and why we used it. So you can learn a lot from those reports. Is there any other questions on what I've covered today? So I've covered bottom friction, eddy viscosity, and the wave mass flux. The wave mass flux is a little bit hard for some people to wrap their mind around, because the idea of having current velocities that go offshore all the time doesn't seem to make sense. Doesn't seem to them that the model is conserving mass, but actually that component, the offshore component, is being balanced by the wave mass transport in the trough and on the wave in the roller. Is there any other questions for today? So if there's no more questions for today, I think I'd like to leave the rest of hydrodynamics for tomorrow, and then go into initial and boundary conditions, salinity transport, and the surface roller tomorrow. I don't know if I mentioned earlier, but the executables and the newest executable is also downloadable from the SERP website. I'll show you where that's at. It should be if you go to webinars in this week's webinar, there's links here to the CMS flow data folder, the CMS wave data folder, the user's guide. This is the PDF that I was going through. Under products, if you click on CMS, you can find the latest implicit code, executables, 32-bit, 64-bit, the DLLs for parallel processing. So I recommend that everybody read the CMS User's Manual. If you have any questions tomorrow, I can answer those. It's pretty lengthy, but it's important. So if there's no more questions, then I think I'll just end the seminar right now. My plan was to do an hour, so I did a little bit more than an hour. And we'll continue tomorrow at 1. Thank you, everybody.